Hey guys, now what we're going to do is we're going to get through some characteristics of exponential functions. An exponential function is a function of the form y equals c to the power x, where c is a constant value that's greater than 0, not equal to 1, and the x is the variable. Now, very quickly here, we see that c has to be greater than 0 and it can't equal 1. This is for a couple of reasons. If I have y equals 1 to the power x, well, we know that no matter what 1 to the is to the power of, 1 times 1 times 1 times 1 times 1, blah, on and on and on, is just going to bring me back to y equals 1, which we consider to be a constant function. The next piece of this is, let's say I had y equals negative 2 to the power x. Now you'll see I'm being very careful with the brackets on this one. If I had the negative on the outside, that would be allowed. But as it stands right now with that negative 2 on the inside, well, if x is odd, then it'll be negative. And if x is even, then it'll be positive. So what will happen in this case is, if we have the graph, instead of getting some nice steady line, it'll be positive point, negative point, positive point, negative point. And what we get is we get a whole bunch of dots that'll be plotted, both positive and negative. They won't be connected, and as it stands right now, we'll say that it's not a function. If you continue on in mathematics and get up to the university level, they'll look at it slightly differently, but for now we're just going to say that's not allowed. So graph each of the following exponential functions, then identify the following: the domain and range, the x and y intercept if they exist, whether the graph represents an increasing or a decreasing function, and the equation of the horizontal asymptote. Now you'll see we have y equals 2 to the power x, y equals 4 to the power x, and y equals 5 to the power x. If you guys want, take these and plot them on your graphing calculator right now and take a gander at how they're going to look. I'm just going to kind of dive in, and I'll use 3 different colors. So the first one that I'm going to do is I'll do this one in black, and y equals 2 to the power x. Now, well, what's 2 to the power 2? 2 to the power 2 is equal to 4, so I have the point 2 comma 4. 2 to the power 1 is 2, so I'll have that point. 2 to the power 1 is 0, and from there that's going to kind of be enough to just get a quick general idea of what my 2 to the power x looks like. Moving on, switching up the color, if I go 4 to the power x, well, 4 to the power 0 is still 1. 4 to the power 1 is 4, and then 4 to the power 2, well, that's going to be 16, which we see is off the graph. So I'm just going to draw that up right there, and I just want you guys to know that there is some curvature attached to this, even though it kind of looks like I'm drawing it straight. Lastly, we'll do this one in green, y equals 5 to the power x. 5 to the power 0 is still 1, 5 to the power 1 is 5, and you see we get again that huge sloping going on right there. So what's happening is, as this number right here, as the base increases, I get more and more curvature, but from there not really much else changes. My domain is just going to be x's in the set of real numbers. My range is going to be y is greater than 0. Now, why is it greater than 0? Very simply, there's nothing I can put a number to the power of that will make it equal 0. Even 2 to the power 0, 4 to the power 0, and 5 to the power 0 all equal 1. X-intercept, well, there's not going to be one because we never cross the x-axis. My y-intercept is always going to be 0, 1 because any number to the power 0 is equal to 1. And my horizontal asymptote is always going to occur at y equals 0. Now moving on, if we do the exact same thing, but now what I'm going to do is I'm going to use a base that's between 0 and 1. So again, we'll start off with my first one, and I'll use black. Now, if I look at this, 1 over 2 to the power negative 1 is going to equal 2. 1 over 2 to the power negative 2 is going to equal 4. Because we remember this negative sign reciprocates what's on the inside right there. So 1 over 2 to the negative 1 will equal 2. And 1 over 2 to the negative 2 will equal 4. 1 over 2 to the 0 will still be equal to 0. And what I have right here is I'll get a graph that looks somewhat like that. Moving on, 1 over 4, 4 to the power negative 1 is 4, 4 to the power, or 1 over 4 to the power 0 is 1. And again, we go like this, and we get something that looks like that. Switching to my last color, 1 over 5 to the power negative 5 is 5, to the power 0 is 0, and again, we get something that looks as such. Now, one thing that I want you guys to notice is realistically, all that we've done is we've flipped the graph. So here, it looks like this, there, it looks like that. This we call an exponential growth. This is what we're going to call an exponential decay. And they share many of the same characteristics. The domain is still going to be x is in the set of real numbers. My range is going to be y is greater than 0. My x-intercept, well, there still is none. My y-intercept is going to be 0, 1. And my horizontal asymptote is going to occur at y equals 0. In general, an exponential function is a function of the form y equals c to the power x, where c is a constant, c greater than 0, c does not equal 1, and x is a variable. If c is greater than 1, the function is increasing. If c is between 0 and 1, we say that it's decreasing. Or increasing we'll call a growth, and decreasing we'll call a decay. And exponential functions of the form y equals c to the x, they all have the same domain, they have that range, they have no x-intercepts, they have a y-intercept of 1, and they're all going to have the horizontal asymptote at y equals 0. I hope you guys have enjoyed.